Hello everyone, welcome to this KANPUR-NPTEL online course on space environment and its effects on orbital spacecrafts. So, during the last few sessions, we discussed the various laws or various aspects of the plasmas and especially the behavior of the plasma when some external electric and magnetic field is applied. So, we have seen if it is an uniform magnetic field. So, a charge particle, a moving charge particle, it starts gyrating about a magnetic field. So, this one we have seen, and what we have done, we have seen that whenever the charge particle is gyrating, its center, that is its moves. So, that is called that is a center is moving. So, we found that there is some x 0, y 0 and there is one function that is z 0 b parallel t. So, as if it is moving or it is guided. So, this is called the guiding center. So, along this is the axis of that is the helical path, and we have seen that what is the radius of the gyration, or it is also called the Larmor radius, and then the cyclotron frequency at what angular velocity it is gyrating. We have seen that if both the electric and magnetic field is present, then in that case, apart from the gyration, it will have a drifting motion, means it will drift in a direction which is perpendicular to both electric and magnetic field. So, we have seen that the drift velocity is given by E by b square, means the velocity vector, that is the and the drifting velocity vector, that is perpendicular to both the electric field and that is as well as the magnetic field. So, so this one I was just telling. So, now, when it is a non-uniform magnetic field, we have seen when the magnetic field either it is converging, when the magnetic field intensity is increasing. So, what happens? There is a phenomena called the magnetic mirroring happens. So, what we have seen that is the magnetic moment, that is mu is equal to So, we have seen that in the last class. So, this magnetic moment is constant, means mu by g is equal to 0. What happens in order to maintain it constant? Suppose if the b has increased. So, in that case this perpendicular component of the velocity, it must also increase. So, that the mu is constant. Now, you see, whenever this should happen, when suppose if this is increasing. So, that in that case the velocity, because the velocity component, I can write the velocity component, it is the parallel component as well as the perpendicular component. Now, if the perpendicular component is increasing, the parallel component must decrease or vice versa. Why this is so? Because this velocity it is not changing. So, in that case, because of this magnetic field line, the increase in the magnetic field intensity, if this component is increasing, this component has to decrease. What does it mean? That the parallel velocity, that is the velocity of the particle which is moving in the direction of the magnetic field, it will decrease, and for sufficient higher values, it will this v parallel, it can tend to 0. 0 means it will stop, but still the force acts on it, and as a result of that it swings back. So, this is called the magnetic mirroring effect. So, it is basically bouncing back and forth. So, this is shown here, it is the magnetic field, you see this is increasing. So, it is bouncing back between these two, this will be the two poles, north pole and the south pole, and this we have seen because of this the trapping of charged particles happens, and this is the reason for the radiation arts radiation belts, that is Van Allen belt radiation belts. So, now we will start that is the effect of the plasma environment on spacecraft. We will have several sessions to discuss in detail how it affects the health of the spacecraft. Well, before that we will see that is what is the origin of the space plasma, that is the in the Earth's orbit, what is the origin of the what are the components of the plasma environment there, and how it affects the spacecraft. We will see that is the whether the plasma environment, how its characteristic is, it differs when you go orbit to orbit. So, as I said, the question is what is the origin of the plasma environment. So, if you remember, that is we discussed in the first module, that is the sun activity and the construction of the sun. So, basically sun is, it is a ball of plasma, it is a very hot ball of plasma. Why? Because of the nuclear fusion what happens in the core of the sun, where the hydrogen atoms fuse to make the helium, and in that process enormous energy is produced, and as a result of this no neutral particles can exist and this becomes all the plasma. So, plasma comes out through different layers, and because of this the sun emits, it is a continuous flow of charges. So, this is called the solar wind. So, this plasma environment in the Earth's orbit, it is a combination of, this is one the solar and other is the terrestrial sources. Terrestrial sources means it is near Earth. So, near Earth that it is again created by the sun, that is by the ionosphere. So, what it does, it create a very dynamic and complex system. So, that affects the space weather, and in turn the space weather, it affects the satellites, its health, and the communication system, navigation system, everything is affected by that. So, that is why the plasma environment is very important to understand how the plasma environment behaves or how it interacts with the spacecraft. So, now we will see what is the solar contribution. Already I told about this. So, solar contribution, it is the solar wind, and the sun is continuously emitting a stream of charged particles. So, this is the solar wind, already we covered it. So, solar wind, and you have seen this wind becomes strong. So, whenever there is the sun activities during solar maximum. So, these are called the coronal mass ejection, then solar flare, then solar energetic particle events. So, at that time the solar wind will become the solar storm. So, there very energetic particles comes, and that also we discussed as a result of this how the magnetic storm happens. Geomagnetic means the geomagnetic storm means our Earth's magnetosphere, and this plasma travels through this interplanetary space and interacts with Earth's magnetic field and the magnetosphere. So, when the solar wind it encounters with the magnetosphere, it compresses the day side, that also we have seen, and stretches the night side into a tail like structure. This interaction, that is the interaction of the solar wind, it can be solar storm also. So, this interaction leads to various plasma phenomena. So, it is including the formation of the bow shock, then magnetosheath and the magnetotail. So, all these terms already we discussed with you. Now, what is the terrestrial contributions? Terrestrial contribution is by the ionospheric outflow. So, what is the ionospheric outflow? So, Earth's upper atmosphere, particularly the ionosphere. So, what is ionosphere actually? Ionosphere, whatever the neutral, there are atmospheric particles, that is the gas particles like the especially the oxygen, it can be the nitrogen, when they are exposed to the ultraviolet light or the X-rays. So, the photo dissociation or photoionization happens. Because of that, those particles that get ionized, and that layer is called the ionosphere. And ionosphere is having different layers like the D layer, then E layer, F1 layer, F2 layer, and this D layer and the F2 layer, they doesn't the D layer will not exist during the night, and F1 and F2 layer will combine into only F layer during the night. So, these layers it generally from something like some 60 kilometers to some 400 kilometers. So, this is called it is the ionosphere or the different layers. So, how this thing happens with the photoionization, this already I said, and there is another is the impact ionization. So, whenever this particles, one ionized particle, it can interact, it can impact with the other, the neutral particle, and it can create also this, it can ionize that neutral particle. So, that is called the impact ionization. So, these processes generate ions that can escape along the magnetic field lines, because as already you have seen the properties of the magnetic field lines, because Earth's magnetic field lines is there, and this charged particles, it is possible that it can get trapped by the Earth's magnetic field and then escapes into the magnetosphere, and this phenomena is known as the ionospheric outflow. So, this outflow also plays a significant role in populating regions like the it is called the plasmasphere and ring current. Ring current already I explained what is the ring current when we are discussing the radiation belt. So, the magnetosphere, so it is a dynamic plasma region. It is dominated by Earth's magnetic field. So, it containing various plasma populations. So, the key regions are the plasmasphere. So, what is a plasmasphere? It is a torus of cold and dense plasma which co-rotates with Earth, primarily composed of ionospheric origin plasma. So, whatever this plasma, it originates from the ionosphere and it gets trapped by the Earth's magnetic field, and it forms like a torus. The formation it is formed because of the magnetic field, this Earth's magnetic field, the nature of the Earth's magnetic. So, this is also, if you see the Earth's magnetic field, a dipolar magnetic field, it forms like a the torus. So, this is the reason, that is the plasmasphere, plasmaspheres, the geometry is like a torus. Also, the radiation belts, this is called the Van Allen belts. So, these are the zones of the trapped high energy particles, mainly the electrons, protons originating from both solar wind as well as cosmic rays. So, this part already we discussed. Then plasma sheet. So, a region of the magneto-tail filled with hot plasma playing a crucial role in the magnetospheric dynamics, especially the geomagnetic storms, and so this plasma sheet they take a a crucial role. So, this is this is the plasmasphere, this is it shows this is a cartoon, and this is the plasma sheet. So, what happens, as I already explained when we are discussing the different phenomena with the solar physics, that whenever there is the magnetic field, two oppositely directed magnetic field, so in between there will be the current sheet. So, here since these are having in the different directions, this magnetic field direction, because of that, so there will be the plasma sheet here. So, it and this already we discussed what is bow shock and what is the magneto sheath and all these things, magnetopause, this thing already we discussed when we are discussing the how the solar wind is coupled to our magnetosphere. So, in that respect we discussed this. Now, we will see what are the effects of the plasma environment on spacecrafts. So, the plasma environment in the space significantly it impacts the spacecraft performance, especially its the reliability and the longevity. So, this is the reason to understand this effects is it is very crucial if you want to design a system which is resilient with the space systems. You have to make the system so ruggedized, so that it can withstand the effects of the plasma environment. So, one very important or very dangerous effect which happens because of the plasma environment is the spacecraft charging. We will discuss in detail, but just I will introduce it here. So, when the spacecraft charging it occurs when a spacecraft it accumulates the charges. So, what happens, the plasma species they get impinged on the spacecraft. We will explain what is the physics, how it gets impinged and how a particular spacecraft gets charged. Basically, a spacecraft gets negatively charged because it electrons basically the accumulation of electrons are more as compared to the positive ions. So, because of this it can lead to various operational issues like the surface charging. So, in regions like geosynchronous or geostationary orbit, the low density, so there we will see that the plasma density is low, but they are having very high energy. So, low density plasmas can cause differential charging. So, we will also explain what is differential charging. Differential charging means different parts of the spacecraft will acquire different potential. So, there will be a potential difference between different parts, and if the potential difference is very high, it can develop a current. So, that is called the discharge current or electrostatic discharge. We will see those things. So, what it will do, because of this it can result electrostatic discharge ESDs, and this ESD is potentially very damaging to electronic components. That also we will discuss in more detail. Then it can happen internal charging. So, what is internal charging? When that is the impinging electrons or even it can be the bit high energetic particle proton also, it can penetrate the spacecraft material. It is so energetic and it can reside inside the dielectric material of the spacecraft. So, what happens because of that, the potential difference inside between 2 points, it can be so high inside the dielectric, it can because of this that is the penetration of charge, and it is staying inside the dielectric material, it can cause an internal discharge. And so here also and in this way it can be it can create the dielectric breakdown, and dielectric breakdown means a lot of the problems with the electronic system. Now, another effect is the photoelectric effect. So, what happens when the ultraviolet UV radiation from the sun, it can also induce the emission of electrons from the spacecraft surface. Again, it depends on the type of the material, its work function. So, it can result into some means those UV radiation, it can excite the surface material in such a way so that electrons are ejected. Electrons, that these particles, they go to a higher energy state and the electrons come out. So, because of this, the spacecraft will become positively charged. So, this balance between the photo emission and the plasma electron collection, it determines the net surface potential. That we will see subsequently mathematically how all those things we take into account in our mathematical modeling. The other effect is called the electromagnetic interference. Whenever there is a plasma, there is a moving particles, there will be the fields generated, electromagnetic field generated, and when it is changing with the time, so it will create electromagnetic field. So, those electromagnetic field, it will work like it will be something like interference or noise. So, this also we will see, and this interference, it will be very detrimental to the onboard system. It can affect the communication system or the sensitive system, where you need a particular level of this that interference should be below some level. So, it may so happen because of this plasma interaction, this EMI thing can go beyond the prescribed or the specified limit, and then it may also damage the onboard electronics, or it can disrupt the communication. So, a signal disruption, already I was talking about this. So, what happens, the fluctuating plasma densities, it can cause the variation in the spacecraft's potential, leading to a noise in the communication and navigation system. Then it can create a problem from the antenna also, because what happens now, a sheath, or already you have seen there is it is called the device shielding, a sheath is formed and it can form around the antennas, and because of that the antenna impedance means we need impedance matching of the antenna to the either receiver or transmitter. But this non-neutral environment, because now the antenna is a non-neutral environment, inside the plasma sheath it is a non-neutral environment, already I explained in the past sessions. So, what will happen? It can affect the signal transmission and reception. Then material degradation. So, exposure to the plasma environment, it can degrade the spacecraft materials over time. Then it can even do the sputtering, the way we have seen the atomic oxygen does the same thing. So, here even a charge, a plasma particle also can do the same thing. High energy ions in the plasma can erode surface materials, leading to mass loss and surface roughening. Then contamination. So, interaction with the plasma can cause the deposition of contamination on the optical surfaces, reducing their effectiveness. There can be thermal effects, because the plasma interactions can lead to localized heating, potentially causing thermal stresses and material fatigue. The other challenges is the attitude and the orbit control system. What happens when a spacecraft gets charged because of the plasma environment? So, you just consider a charge is moving in a magnetic field. So, Earth having magnetic field. So, whenever a charge is moving in the magnetic field, already you have seen there is the Lorentz force on it. Force means that force will it can change its attitude, or even it can change its orbit. So, in that case it will complicate the attitude control. Then power system. Plasma interactions can cause the differential charging on the solar arrays also. So, if that happens, it will lead to the power loss or even damage. Then sensor accuracy. Plasma induced noise, it can affect the accuracy of the onboard sensors. So, if there is a very sensitive instrument you are using, so this whatever the plasma induced noise means, it is something like again this electromagnetic interference, it can affect this sensors, and then it can impact. So, what does it mean? It will impact the mission data quality. So, now we will see the plasma environment at different Earth orbits. We will consider the low Earth orbit, medium Earth orbit, and the high Earth orbit. So, what is the characteristics of the plasma environment in low Earth orbit? So, here this low Earth orbit. So, low Earth orbit plasma environment is basically it is dominated by the ionosphere. Especially it is, if you consider this F2 layer, which will be around 300 to 500 kilometers. So, this is characterized by high density low energy plasma. So, electron temperatures typically they ranges from 0.1 to 0.4 electron volt, and the ion densities they can peak 10 to the power 10 to 10 to the power 11 ions per meter cube. So, dominant ions in the low Earth orbit is atomic oxygens O plus, and the altitude is between the 300 to 500 kilometer. What I say is the F2 layer. Then the relative motion effects. Now, a low Earth orbit spacecraft, it is the average velocity is 7.8 kilometer per second. It may expose the spacecraft to a stream of atomic oxygen at energy approximately 5 electron volt. So, this also this is sufficient for causing the drag on the spacecraft. What are the operational implications in the low Earth orbit? Again here the spacecraft charging. Of course, here since the charged particles, this plasma is having lower energy, this there is the risks of differential charging is not there, but the high voltage systems such as solar arrays, it can still experience parasitic currents and potential arcing. Whenever the high voltage systems, even a low density plasma can create havoc. Then plasma drag, already you have seen this, this one, the last relative motion effects. So, interaction with the ionospheric plasma result the drag forces that can alter the satellite orbits over time, necessitating periodic adjustments. Then the medium Earth orbit. So, this is the orbit, the altitudes. So, here the plasmosphere and the radiation belts are there, and it encompasses part of the Earth's plasmosphere and the Bellon radiation belts. So, these regions they contain especially the Bellon belt radiation belt, high energy charged particles, primary electrons and protons trapped by Earth's magnetic field. So, that is why from the point of view of high energy particles, it is this medium Earth orbit satellite, because since it is within the Bellon radiation belt. So, there can be the effect like internal charging and those things. Then the variation of plasma density. This plasma density in the medium earth orbit is varies due to factors like the solar activity and geomagnetic storms. So, this during this solar activity, what happens, this valence belt, radiation belt, those the the particles energy and all these things, it changes very fast. So, in that case it can also create the problem for the spacecrafts. So, we will see what are the implications. So, differential charging here it can occur, which we have seen that it may not occur in LEO, but here it may happen, and differential charging means there is the risk of the electrostatic discharge. Then as I said, since there is high energy particles in the radiation belts, internal charging can happen. Now, the high earth orbit HEO, it is the orbit, basically the geosynchronous orbit and geostationary orbit. So, that will be equal to this. Generally we used for our earth satellites, we use so this is GEO and GSO. GEO means geostationary and geosynchronous is GSO. So, what is the characteristics? Here the characteristics, it is it lies within the magnetosphere where the plasma density is significantly lower, but the particle energies are much higher. It can have several kilo electron volts, especially during the magnetic storm. What are the operational implications? So, here again the spacecraft charging, especially the differential spacecraft charging can happen whenever in the high earth orbit, especially during the geomagnetic storm. We have seen, we have introduced what are the effects of the plasma environment of spacecraft. So, the next session onwards we will discuss it. We will try to understand how a spacecraft gets charged, how it gets negatively charged or positively charged, what is the physics behind it. So, these things we will be studying, and at the end we will study what can be the mitigation techniques. So, thank you very much.